When you flip a light switch in your home, um, the electrical signal travels at nearly the speed of light. Like you click a button and boom, instant illumination.
Right, it's just immediate.
Exactly. And we instinctively picture the electricity powering our devices as this incredibly fast, zooming current of energy. But what if I told you that the physical reality, like the actual electrons moving through the wires in your walls, are traveling slower than a garden snail?
It really shatters that ultimate modern illusion, doesn't it? I mean,
Ah.
we associate electricity with instant gratification, completely ignoring the sort of brute force physics happening just millimeters beneath our fingertips.
Yeah, it really does. And welcome to today's deep dive, everyone. Our mission today is demystifying the hidden physical reality of how electronic circuits actually function.
Which is such a fun topic.
It is. We are pulling apart a 14-slide presentation titled Part 12A Circuit Fundamentals. And we're basically going to translate the abstract math of physics into, the real world reasons why your laptop burns your legs when you open too many tabs.
Or why your phone battery degrades over time.
Right. And what is actually happening inside your charging cables.
Hmm.
By the end of this deep dive, you're going to realize that almost everything you intuitively assume about how fast electricity moves is just completely wrong.
It's about peeling back that sleek user interface, you know,
Mhm.
and looking at the raw, kind of chaotic plumbing of the digital age.
And plumbing is actually a great place to start because looking at slide one, the source material kicks things off with the most classic, fundamental image in electrical engineering. It's just a basic loop,
Yeah, a battery, a wire, and a light bulb.
the holy trinity of circuitry. You've got flow, resistance, and power.
Honestly, if you can grasp how those three interact in just a simple light bulb loop, you hold the keys to understanding everything from like a digital watch all the way up to a supercomputer.
So, to visualize it, moving to slide two, the presentation uses a water to wire translation, a water tower analogy,
Oh, I
basically.
love this analogy. It's so helpful.
Yeah, so voltage is the water pressure, like the push coming from the sheer height of the water in the tower. Current is the actual volume of water moving through the pipe, and resistance is a bottleneck.
Like the width of the pipe or maybe a kink in a hose restricting the flow.
Right. It's a brilliant grounding tool for the absolute beginner.
It really is. Like you kink the garden hose, resistance goes up, flow rate drops. If you want that same flow back, you have to crank the spigot, which is increasing the pressure or the voltage.
Okay, but before we talk about kinks in the hose, looking at slide three, we need to talk about what is actually flowing: electric current.
Measured in amperes or amps.
Exactly. The source notes that 1 amp is 1 coulomb of charge passing a point per second.
Right. So think of a coulomb as just a massively large standardized bucket of electrons. 1 amp means one bucket of electrons is moving past a specific checkpoint in the wire every single second.
Wait, hold on. I need to stop us here because I'm looking at the slide's breakdown of current and the math completely contradicts the physical reality.
Ah, yes. I know exactly what you're looking at.
Is there a typo in these notes? Because it says physical electrons carry a negative charge, so they are repelled by the negative side of a battery and flow toward the positive side.
Yep, that's the physical truth.
But then the formula for conventional current tracks the flow as moving from positive to negative. Why on earth are we tracking this backward mathematically?
You've just stumbled onto one of the most frustrating and frankly kind of hilarious historical blunders in all of science. We could basically blame Benjamin Franklin for this one.
Wait, Benjamin Franklin, like the kite and the key guy?
The very same. Hundreds of years ago, long before we even conceptualized what an electron was, scientists observed that something was moving through conductors. And Franklin just made a 50-50 guess.
Oh no, let me guess. He picked wrong.
Spectacularly wrong. He assumed the moving charge was positive, flowing from a surplus at the positive end to a deficit at the negative end.
Oh,
Yeah, and by the time the electron was actually discovered in the late 1800s, and physicists realized the moving particles were negatively charged and flowing the complete opposite way, it was just too late.
too late. How?
Well, all the foundational math, the textbooks, the engineering standards, they had all been written using Franklin's backward convention.
That is wild. It's like an entire global infrastructure agreeing to drive on the wrong side of the highway just because the first map maker accidentally mirrored the drawing.
It really is.
Uh,
So to this day, mathematically, we track current as moving in the same direction as the electric field, from positive to negative.
Even though the physical reality is that the electrons are swimming upstream against that mathematical current.
Exactly. It's totally backwards.
Well, that perfectly highlights the danger of simplistic analogies, which brings me to a major issue I have with the water pipe metaphor we started with on slide 2.
What's the issue?
It makes it sound like wires are just empty, smooth, hollow tubes that electrons glide through. But transitioning to slide 4 here, looking at the atomic breakdown, that is absolutely not the case, is it?
Not even close. If you zoom into the atomic level of a copper wire, it's not an empty hallway at all. It is a chaotic, dense, violently vibrating forest of copper atoms locked into a lattice structure.
The slide calls it the obstacle course.
That's a perfect name for it. The electrons are essentially trying to sprint through a mosh pit.
The diagram shows these little electrons constantly crashing into the massive atomic lattice of the conductor.
And this is where the physics translates directly into your daily life. Every single time an electron collides with an atom in that lattice, its electric potential energy drops.
Right, because it hit something.
Exactly. But that energy doesn't just vanish, right? It is physically transferred into the atom, causing the atom to vibrate faster.
And microscopic vibration is literally what heat is.
Precisely. This is the exact mechanism of why the computer you're listening on right now gets hot.
Oh, wow.
Yeah, when you open a heavy video editing application, your device demands more current to process the data. More current means more electrons trying to squeeze through that atomic mosh pit per second.
Which means more collisions.
Millions of additional collisions,
Mm-hmm.
dumping kinetic energy into the lattice, vibrating the material until you physically feel the heat on your lap. It is the literal physical friction of electricity.
It's incredible to think of it as physical friction rather than just, a mysterious side effect. So if that's the reality of resistance, how do we mathematically measure it?
Well, moving to slide 5, that's where we get into visualizing the math.
Right. The slide breaks down the formula for resistance, measured in ohms, relying heavily on physical dimensions. They use a milkshake analogy here.
Oh, yeah, that's a good one.
High resistance is like trying to drink a really thick milkshake through a long, skinny drinking straw. You've got a long length and a small area. But low resistance is like drinking through a short, wide drain pipe.
The wider the physical road, the more lanes the electrons have to travel down without bumping into those obstacles we just talked about.
Which explains why jumper cables for a car battery have to be so incredibly thick. If you tried to pull that massive surge of current through, say, a thin little phone charger wire, the friction would instantly melt it.
Exactly. The density of collisions would cause the temperature to spike past the material's melting point in a fraction of a second.
So, okay, moving on to slide 6. If resistance is constantly fighting the current, basically stealing energy as heat, there has to be something violently shoving those electrons back into the fight to keep the device running.
Right, something has to be doing the pushing.
And the presentation labels this electromotive force, or EMF, provided by the battery, but I feel like the terminology is trying to trick me again here.
How so?
Well, it says force. Is there like a tiny physical force, like a microscopic piston physically pushing these electrons?
I'm really glad you're skeptical, because the terminology is completely misleading again. Electromotive force is not a physical force at all.
See, I knew it.
Yeah, it's not measured in newtons, like gravity, or a physical push.
Yeah.
It is an energy per unit charge quantity measured in volts.
Okay, let's make that concrete for the listener. It's not a piston. What is it? Like a ski lift?
That is a phenomenal way to picture it. Think of the chemical reactions inside the battery as the motor of a ski lift. It does work on the charge, lifting it from a low potential energy state at the bottom of the mountain to a high potential energy state at the peak.
And once the electron gets off the lift at the top, it enters the wire circuit.
Yes, and as it skis down the bumpy mountain, which is the obstacle course of the wire, it bounces off atoms, losing that potential energy to physical resistance.
And the slide calls that loss the potential drop.
Exactly.
Hmm.
The EMF's job is simply to maintain the ski lift, constantly pulling electrons back to the top of the potential mountain to keep the continuous loop going.
That makes the math of Ohm's law, looking at slide 7 now, so much more intuitive. Voltage equals current multiplied by resistance.
V equals I times R.
Right, but the presentation is careful to note that this straight line math is an idealized model for what they call ohmic materials, like standard high quality wires where current and voltage scale together perfectly on a graph.
But as we know, the physical world doesn't always play by idealized rules.
Definitely not. And to explain why, slide 8 introduces something called the band theory matrix. This seems to be like the fundamental dividing line between different materials in the universe. Can you unpack what we are looking at here?
Sure. So band theory answers the ultimate question. Why is copper a great conductor, but a piece of rubber won't let electricity flow at all?
Okay.
It comes down to quantum energy levels, these bands where electrons are allowed to exist within a solid. The source divides this into three categories. First, you have metals.
Like copper.
Right.
Yeah.
In metals, the energy bands where electrons normally live overlap directly with the conduction bands where electrons are free to move.
So the door is just permanently open.
Exactly. Electrons can wander freely through the lattice with almost no applied energy.
Got it.
Then, on the complete opposite end of the spectrum, you have insulators, like rubber or glass. Insulators have a massive band gap.
The band gap.
Yeah, there's a huge quantum chasm between where the electrons are trapped and the conduction band where they need to be to actually flow. Under normal conditions, they simply cannot cross it.
But sitting right in the middle, we have semiconductors, like silicon, the literal foundation of Silicon Valley.
And the birthplace of all modern computing.
Right.
Semiconductors have a band gap, meaning they aren't natural conductors. But the gap is really small.
Small enough to jump.
Exactly. It's narrow enough that if we apply very specific controlled conditions, a precise voltage, a burst of light, or a specific heat, we can give those electrons just enough energy to jump the gap. We can instantly switch the material from an insulator to a conductor and back again.
Wow. That binary control on or off, 1 or 0, that's digital code.
That is the physical basis of every single software program ever written.
That is mind-blowing. And speaking of applying heat to semiconductors, moving to slide 9, this brings up my favorite part of the entire source text, the heat paradox.
Ah, yes. This is a fun one.
So we established earlier that heat is atomic vibration, right? So if a material gets hotter, the atoms are vibrating more violently. The mosh pit is getting crazier, making it harder for electrons to get through.
Which means resistance should logically go up.
Right.
And in standard ohmic conductors like copper, that is exactly what happens. Heat increases resistance.
But the slide explicitly points out that in non-ohmic materials like graphite or those semiconductors we just talked about, they behave oppositely. The resistance actually decreases when the temperature goes up.
It's so counterintuitive.
How is that physically possible? If the obstacle course is vibrating more violently, how can the flow get easier?
It seems like a complete contradiction until you remember the band gap we just discussed. In a semiconductor, heat isn't just friction. It is a vital form of thermal energy.
Oh, I see where this is going.
When you heat up a semiconductor, you are injecting raw energy into the material. That energy excites the trapped electrons, giving a massive number of them the exact quantum boost they need to jump across that small band gap.
Oh, wow. So even though the course itself is getting bumpier and harder to navigate, you are simultaneously unlocking millions of new runners to enter the race.
Perfectly stated. The sheer volume of newly freed electrons jump in the gap completely overpowers the negative effect of the vibrating atoms.
That's so cool.
Yeah, so the overall resistance plummets and conductivity spikes. It is a brilliant quirk of quantum mechanics, but it's also a nightmare for engineers.
Ah,
Because if a computer chip gets too hot, it drops its resistance and starts conducting electricity across pathways it shouldn't, causing the whole system to crash.
that makes total sense. Okay, let's take all this quantum weirdness and bring it back to the physical source of the power itself on slide 10, the battery.
The good old battery.
The slide compares ideal versus real batteries. In a physics textbook, a 12-volt battery delivers exactly 12 volts of push. But the diagram for the real source has a tiny resistor drawn inside the battery box itself.
Because we have to remember that a battery isn't a magical portal that summons energy from another dimension. It is a physical object made of physical matter, chemicals, metals, thick electrolytes.
Right.
And just like the copper wire, those internal materials have their own natural resistance to the flow of electrons.
The slide calls it the internal toll. The power has to pay a physical tax just to escape the chemical sludge of the battery.
We represent this internal resistance with a lowercase r, and it basically causes a voltage drop before the current even reaches the external metal terminals.
Which perfectly sets up slide 11. Calculating power measured in watts. Power is the rate of energy transfer. The source gives us a specific variation of the formula here. Power equals current squared multiplied by resistance.
P equals I squared R.
Right. Why is that specific arrangement so important, like the math of heat?
Because that specific mathematical term describes the exact rate of energy loss due to physical friction inside the material.
Oh, tying it back to the heat we discussed earlier.
Exactly. Earlier, we talked about devices getting hot from lattice collisions. Well, the I squared R equation calculates exactly how much electrical energy is being sacrificed as physical heat, whether that's inside a computer processor, a wire, or inside the battery itself.
Okay, so we have all the pieces now: the atomic obstacle course, the ski lift of EMF, the band gaps, the internal chemical toll booth. Let's put this all into
Let me
practice.
do it.
Slide 12 gives us a recipe card of applied physics to close this out. Let's look at this scenario. We have a massive 50-meter length of 18-gauge copper wire carrying 1.67 amps of current.
Let's just pause and actually look at what that means. 50 meters is half the length of a football field.
That is a long wire.
We are talking about a significant distance to push a physical current through a solid metal lattice.
And the math walks us through it. The expert breakdown here says we calculate the voltage drop over that entire 50-meter distance, and it turns out to be only 1.75 volts.
Yep.
Then we find the total resistance of that massive wire, and here's the shocking part. The total resistance is just 1.05 ohms.
Which is astonishingly low. It proves exactly why copper is the gold standard for global electrical wiring.
Because it's so efficient.
Right. You can push a substantial current across half a football field, and you only lose a tiny fraction of a volt to the obstacle course. Its bands overlap so perfectly that it creates an incredibly efficient atomic highway.
But how fast are the cars actually moving on that highway? This brings us to slide 13 and the ultimate aha moment I promised you at the very beginning of this deep dive.
The big reveal.
We've established that the signal travels at the speed of light, but now we are going to calculate how fast the physical negative electrons are actually traveling through that 50-meter copper wire. The math on this slide calculates what is known as drift velocity.
So we take the same 18-gauge wire, the same 1.67 amps. We calculate the current density, factoring in the massive number of free electrons available in copper's conduction band. And then we solve for the physical speed of the particles.
Drum roll, please.
The drift velocity is 1.5 times 10 to the negative 4 meters per second.
I really want you, the listener, to let that number sink in. 1.5 times 10 to the negative 4 meters per second.
It's tiny.
That is a fraction of a single millimeter per second.
It is quite literally slower than a snail.
You flip a switch and the light instantly turns on. The wave of energy pushing through the system travels at nearly the speed of light, but the physical electrons themselves, the actual charged particles,
Barely moving.
they are fighting through that atomic obstacle course at a microscopic crawl. It would take a single electron hours, maybe days, to travel from the switch on your wall to the bulb in your ceiling.
It forces you to completely reevaluate what electricity even is. You aren't shooting an electron through a wire like a bullet from a gun.
Right.
It's more like a pipe completely packed edge to edge with marbles. When you violently shove one marble in at one end, a different marble instantly pops out the other end.
Ah, I love that analogy.
The push, the wave of force, transfers instantaneously through the line, but the individual marbles themselves are barely inching forward.
That completely changes how I visualize the wires in my house. Okay, let's look at the final slide, slide 14, real battery power output. We have a 12-volt battery with 2 ohms of internal resistance running a circuit at 2 amps.
First, we calculate the total energy conversion. 12 volts of EMF multiplied by 2 amps gives us 24 watts of total power generated by the chemical reaction.
But then we hit the internal toll boost we talked about, the power loss to internal resistance, our I squared R formula.
Right. 2 amps squared is 4, multiplied by the 2 ohms of internal resistance gives us 8 watts of power entirely lost.
So we subtract the loss. The battery's chemicals create 24 watts of energy, but it loses 8 watts just fighting through its own internal sludge.
Exactly. So the net power output, the actual usable energy successfully delivered to the rest of your device, is only 16 watts.
It's a massive energy tax.
Yeah.
You buy what is mathematically a 24-watt battery, but you only ever get to use 16 watts of it.
And remember, those 8 lost watts do not magically disappear into the ether.
They become heat.
Yes, they convert directly into kinetic energy, vibrating the lattice of the battery itself, which is exactly why, if you continuously draw high current from a battery, the physical casing gets warm, or even hot to the touch.
Wow. So let's recap this incredible journey. We started with a simple water pipe analogy, only to realize that wires are actually chaotic atomic obstacle courses where electrons bounce like pinballs, causing the physical friction that overheats our laptops.
Right.
We unpacked how heat can paradoxically make semiconductors perform better by injecting them with enough thermal energy to jump the quantum band gap. We calculated the internal energy tax hidden inside the chemical sludge of every battery. And, most mind-blowing of all, we calculated the microscopic cosmic crawl of the actual electrons powering our world.
If we connect all of this to the bigger picture, I want to leave you with one final thought to ponder, based directly on the extreme slowness of that drift velocity on slide 13.
I'm ready.
Think about the massive power station generating electricity miles and miles away from where you are sitting right now. Because physical electrons only move at a fraction of a millimeter per second, the electrons currently being pushed through the turbines at that power plant will likely never, ever reach your house.
Wait, really?
Truly, when you pay your utility bill, you are not paying the electric company for the physical delivery of specific electrons to your home.
Oh, wow.
The electrons inside the copper wires of your house have always been there, built into the atomic lattice of the metal, just waiting in the dark. You are simply paying the power company for the near light speed wave of energy they transfer, as they force all those electrons to slowly bump into one another across miles of grid. You are paying for the push, not the particles.
You are paying for the push, not the particles. That is going to stick with me for a long time. Well, thank you so much for joining us on this deep dive. Next time you pick up your phone or feel your laptop getting a little warm, take a second to appreciate the chaotic, microscopic obstacle course happening right beneath your fingertips.